Whenever you're ready, Justin, it's all yours.
Thank you so much. Thanks for having me. My name is Justin. I'm a third-year PhD student at Georgia State University. And like it was said, my project focuses on measuring distances and constraining galaxy masses for 24 nearby Seyfert 1 AGN host galaxies that all have direct black hole mass measurements from reverberation mapping, or RM, because that's the only time I'm going to be able to say that phrase today. The reason why I'm focusing on measuring distances is because there are only 6 AGN host galaxies that have distances of any quality that are independent of their redshifts, which means that for all the other galaxies, any derived quantities that directly rely on distance, like mass, like luminosity, are all affected by the uncertainties in the distances caused by the local peculiar velocities. And since most AGNs are hosted in spiral galaxies, they make the perfect candidates for the Tully-Fisher relation. And the first step of the Tully-Fisher relation is measuring rotational velocities. And so we've done that by observing a set of 21 centimeter H1 emission lines back in 2013, and then I observed a second set in 2018. And because we're looking to measure rotational velocities, we're limited to the emission lines that exhibit the classic dual horn profile, or the Batman profile, as I lovingly refer to it. So that limits us to 24 galaxies that we have constrained rotational velocities for. And the next step is measuring galaxy magnitudes. These are Seyfert 1 galaxies, and so we have to worry about the AGN brightness contaminating the galaxy brightness, which is the thing that we want to measure. We want to measure the stellar light, the thing that's tracing out the mass. And so we need to separate out the different sources of light, and the way that we've done that is with surface brightness decompositions using GalFit. And so we've constrained each of the brightnesses of the morphological components separately, which means that we have a constraint on just the galaxy light separate from the AGN light. And we've been able to do this with all of our targets, which means that we have 24 Tully-Fisher distance results, 15 of which are the first redshift independent distances that are in the literature. And for 15 of these, we're able to make multiple distance measurements, which is what this plot is showing here. For all of our targets, we have HST V-band images. And then for 15 of these, we have additional ground-based observations in B, V, R, I, and H bands. And that's what this plot is showing here. We compared the HST-based distances on the x-axis and then the ground-based observations on the y-axis. And so now we have distances, we have rotational velocities, and we have the spatial extents of these galaxies. We can now start looking at the different masses in these systems and compare them to the RM-based black hole masses. If the H1 emission lines allow us to constrain what the total gas mass is, and we compare that to the black hole mass in the left panel here, and we show a weak correlation. If we add the stellar masses to our gas masses, we have a constraint on what the total baryonic content is. That's very similar to the project that we did last year, which is cited below. Here we've just updated our stellar and gas masses with our new distances, and you see that the relation is virtually identical. If we use the radii of the H1 disks and the rotational velocities, we can constrain what the total gravitational masses are, or the dynamical masses, and compare that to the black hole masses. And we do see a correlation, albeit with a sizable scatter. And finally, if we subtract away the baryonic content from the gravitational masses, we have a constraint on the matter that we can't directly detect, or the missing matter, or the dark matter. And we compare that finally to the black hole masses in the right-hand panel. And we do see a correlation with slightly less scatter than the dynamical mass relation. The thing to keep in mind, though, is that we are using the H1 radii to constrain these masses. And we know that the visible radii underestimate the true radii of these galaxies, or effectively the radius of the dark matter halo. And so what we've done here is scale up our H1 radii by observed relationships between the visible and the virial radii, or the radii at which the densities hit 200 times the critical density of the universe, or effectively the radius of the dark matter halo. And so we've scaled those up, we've recalculated our masses to estimate what the total masses of these systems are, and we call that the halo mass. And finally, we plot that against the RM-based black hole masses. The black line is our best fit, and we've compared that to several different scenarios. The red and blue lines are observationally constrained relations between total gravitational mass and black hole mass. And finally, the green dotted line is from the hydrodynamical illustrious simulation of halo mass to black hole mass, which we show good agreement with, especially in the slope, but we find excellent agreement with the observationally constrained relations. And that's all I have to share with you today, and I'm happy to take any questions.
Thanks very much. That's a very cogent presentation, Justin. Um, this business of uh, calculating distances is both very important and both very difficult to do. And so, do you want to comment on how your methods compare to existing results in the literature where you can do the comparison?
Sure, sure. There are only a couple, but it's actually very interesting. So the first one that was recently measured just a couple of months ago was a Cepheid-based distance to a nearby AGN host, NGC 6814, shown here, and the emission line here. That Cepheid distance was just about 22 megaparsecs, and our Tully-Fisher distance with all the bands shows excellent agreement within the uncertainties. There's another galaxy that's of interest that has a companion that it's interacting with that has a distance constrained from surface brightness fluctuations. That's about 24 megaparsecs. And ours is very close within the uncertainties, which it should be if they're interacting. And the previous Tully-Fisher distance is closer, which it should be because we're taking out the AGN light, which means that we're dimming the galaxy to be at its true galaxy-only luminosity. So we should be pushing it further, which we are. So all good sanity checks.
Right. So, do you have any, like, are you going to expand your sample? Where are you going with this?
So this is our sample as it stands right now. The Tully-Fisher relation was the best one to use for the largest sample of AGN hosts because they are spiral galaxies, so we can trace out the rotational velocities pretty easily with just a single emission line. The other ones, if they're hosted in early type galaxies or they're too far away for the H1 to detect, or for ones that are too face on so that we don't get the dual home profile shape, which means we can't recover the rotational information for. Those are all separate programs happening simultaneously. Some are being targeted for Cepheids, some are being targeted for galaxy cluster luminosity functions. So this was the let's measure a bunch of distances, and then the rest of the outliers are being taken care of in separate tangential projects.
Okay.